Hi there, welcome back to Triplicate, and in this video we're going to move on with our super rechargeable battery tester cum charger. And as promised, I have set up two battery holders, decent quality ones for a AAA and AA. And what I've done, instead of connecting them in parallel and then I mean, goodness knows what happened if you put a battery in each and then somehow connecting it to get across an 18 volt drill battery and blowing everything up. There are a socket for each battery and a socket that's not, and a plug that's not so easy to get out, but there you go. And that's got the battery charge positive, the battery charge negative, and the sense positive and the sense negative. And eventually we will have the drill battery chargers will have these sockets on them, and these socket plugs and sockets are cheapo. Well, they're supposed to be automotive, but I'm not sure I'd trust them in an automotive application. Well, they're cheap and they're fine for this because it's just a research and development application. Anyway, I've also, with the old setup, gone through all the batteries I had, the good ones and the bad ones, the ones that I thought were duff, and I found one good one that was bad and one bad one that was good. Apart from that, they were as I'd expected. So first thing, I think we'll look at some of the results that I got off some of the batteries and just mull over our findings on how nickel metal hydride batteries work and wear out. Okay, so I have taken all my batteries, given them numbers on, yes, painted the number on the battery, and got a spreadsheet. Sad anarchy person I am. So let us look at AA battery 10, which is a good battery. It's the measured capacity is 2416, again against 2500 with 0.18 of an ohm resistance, and AAA, these top ones, 23, which is 508 milliamp hours when it should be against 750 quoted, and nearly 2 ohms internal resistance. That's red because that's a bit dodgy, but might use it in clocks and things where it's not critical. So if we fire up, okay, so this is AA10, and we are interested as much in the way it charges up as anything else. And you see here it's charged up. When I initially put it in, it's charged up to a pretty constant level, and then sat there. And I may well eventually have had to skip on. And remember, here I put 1.55 volts in it, so it's got to get to there before it says it's fully charged. So, and then it discharges nicely down here, and it charges up again. But here it seems to charge up to a constant level and then go up at the end, and here it has got up to our 1.55 volts quite smartly. And I'm sort of beginning to think that that might be a temperature effect. So when I initially charged it, it was probably in the middle of the afternoon, and then it was cooler in the morning when it charged up the second time. So now let's look at AAA 23, and it covers more of the display, but it's the same sort of thing. And you can see that the gap between the yellow is the voltage, the run voltage, i.e. when it's charging or discharging, and the green is the monitor voltage when we just let it sit for 10 seconds and let the voltage settle. And you can see, oops, when it's discharging, the voltage under load really dies once it gets empty, which means that if it's in an application that draws any kind of current, it's probably going to fail before it's what I've called its rated measured capacity of 500 milliamp hours, purely because the internal resistance is so high, and you get these weird effects where the internal resistance drops once I've started charging it up again. No, okay, and here's a bad one, and you can see the problem really is the resistance. Now it even goes off the top of the normal scale I use. I mean, you see the resistance, that is the difference between the voltage charge and discharge and the voltage just monitored, is huge. And you even get this weird thing here where under load the voltage actually comes up as it discharges. Don't know what's going on there. And if we analyze that, here's the analysis, and we get a capacity of nearly 1800, and I can't remember what the battery was quoted at, but it's not bad. It's not bad. I mean, that's probably, I always reckon, 2/3 of the quoted capacity, and it's usable. But you can see here the voltage, the internal resistance is 1.54, and as I say, you get all these weird effects. So let's have a look at another one. So here we have a AAA 1000, I've actually recorded that, which says it's bad with low capacity, so let's have a look at that one. Again, you see quite high internal resistance, and as you can see the discharge voltage just drops like a stone instead of dropping, levelling off and then dropping again, which is probably indicative of something. So if we analyse this again, yeah, we get 436, so it's less than half the rated capacity, and the internal resistance is over 2 ohms, which is not good. I've been reckoning 1/3 of an ohm for a AA and 1 ohm for a AAA is acceptable in terms of internal resistance, but that's just me thinking up an arbitrary number. Okay, so here I've plotted out one of the batteries on a spreadsheet so we can get some axes. Okay, the first thing to note is that the y-axis is inaccurate due to some bug in the way it logs the data, which I am going to look into shortly. But we can see here the red trace, it gets up to what's actually logged at 14.45, but should actually be 14.5, if I'm making sense here, which is where it wants to be, so it then switches into discharge mode. But here it gets up to just up to 15 dead and sits at that level and never gets any further. And I guess here I probably just skipped on manually, realised it wasn't going to get any further, and I think that discrepancy is due to the fact that the fully charged voltage is temperature dependent, but don't quote me on that, I'm not sure. So what I've decided is that if the monitor voltage on charge doesn't get any higher for an hour, that's 12 readings, then we say, yeah, okay, it's fully charged, and we move on to the next section, whatever it is. Okay, so let's implement that and see how it works. Okay, so we want to test our nickel metal hydride charging setup, so I've resurrected the high-tech charging tester, which now features one of these plugs on it, so I can just plug it straight in, which is nice, and that goes off up here to the 10 power supply, which is currently set so that we have 2.6 some volts across our, in inverted commas, battery. So let us see how it performs. Okay, so we've set our battery up to be nickel metal hydride, and we've got 2 cells and 1000 milliamp hour capacity. So we will send those settings. Okay, and we're ready to go at that. So we will clear the output and we will set it going. Like that. And we actually want to look at this because it'll tell us what's actually going on. So I'm now going to, you might see my elbow, start cranking the voltage up. Quite slowly maybe, and I've got it running on fast mode. So it's updating every few seconds, not every 5 minutes, because otherwise debugging and testing would take forever. So it's set so that at 3 volts, that's 1.5 volts a cell, it thinks, oh, am I charged? So it's now started a timeout, which is an hour normally, which is 12 periods. And if it doesn't get a higher value for an hour, it says higher value of the voltage, the monitor voltage. As it charges for an hour, it says, well, the voltage isn't going up, so we're fully charged. So that's, you see, it's counting down 13, 12, 11. But if I now put a higher voltage in, there, it resets it and starts the timer again. So again, we'll do it again. Why not? Okay, so let's just reset again. And then if we leave that for its hour, okay, and 1 is the timeout value. So the next time you should do the relay click and it'll go into monitor mode. There we go. Timeout, and it's gone back into monitor mode. And if we look at the graph of it, there, it's gone into monitor mode. And it does have an upper limit, so if we just quickly run that again, action, run. We'll go back to here again, and I will start cranking that up again. Okay, and it's got into the timeout, but we're not going to let it time out. We're going to continue to increment the voltage, increase the voltage. Yeah, set this to 1.7 volts or so, but would normally set it to 1.6. So 3.4 we're looking for. And there we go. So it's not timed out, it's just got to the cut-off voltage. I don't know, just to stop it, the really tough battery ramping the voltage up forever and cooking it. Okay. So that seems to me to be working, so perhaps it's time to put the code back to normal run mode and try it on a battery. So let's do that. And there it is, back in its little corner and ready to rock with a rail battery in it, ready to test. So we'll fire that up and see how it goes. Okay, so I have implemented the special nickel metal hydride charging scheme. Okay, so yes, as well as constant current charge, constant voltage charge, we now have a special nickel metal hydride charge type. And you can see it only has a timeout. It picks its parameters from the capacity and the number of cells. And this is the result. Again, not quite what we would expect because of the rounding errors in the logging. Again, which I will come to in a minute. But here you can see it charges up. It's already pretty much charged to start with, and it charges up straight up to 15.5 volts, 15.6 volts, and goes into discharge. And here you can see it charges up gently, then goes up, as I said, quite quickly, and sits at a level, and that level is here. I've highlighted these. Again, the numbers aren't exactly because of our rounding errors. So it's got to 1507 millivolts, and then it's not gone up again for the next 12 or 13. So at the end of that it said, oh, I'm charged, and just dropped back into monitor mode. So I think I am happy that that works. Okay, so what we put in our log is two voltages: the monitor voltage, the mon, that's the voltage with no charge or discharge, and that is 15 bits. V-run, the charging or discharging voltage, that's 15 bits, i.e. 0 to 32 odd thousand millivolts, 32 volts. The current, which is up to an amp in milliamps, so that's 1024, that's 10 bits. And the mode, which is 0 to 6, which is 3 bits. So the original scheme was 32 bits, so that's 3 bits here. This was chopped down to 7 bits. So we lose, so that's increments of 8 milliamps, and these were chopped down to 11 bits, which is minimum resolution, probably a better way of putting it, of 16 millivolts, and we are interested in less than 10 millivolts.
So that is why we've had problems with the logs. So if we add all those together, we get 32 bits, or one 32-bit number, and we had 1,000 of those. So what I've done is I have changed it. So this is in 16 bits, so we have 1 bit unused. This is in 16 bits, again 1 bit unused. And this are also in 16 bits, so we have 3 bits unused. So that is my new scheme of doing it. So we get 6 bytes or 48 bits. And I have had to reduce the log size from 1,000 entries to 750 entries because I've only got 8K of RAM in the good old Arduino. However, it is 5 minutes, 1 entry every 5 minutes, that's 12 entries an hour, so we have 750 over 12, which is Casio's finest. 750 divided by 12 equals 62.5 hours, which is again divided by 24, 2.5 days. Now I don't really want to run it for more than 2.5 days. I suppose we could conceivably do some cycle it several times, but for now we're going to say that's absolutely fine. And I have implemented that and it does work. Well, I'm going to call it for this video at this point. I was going to go on, but I've got to go and paint the boat, so try and get this one out and return to this topic when I get home. I do have a few bug fixes and improvements to the software which I'm also going to make, and I'm also going to look, having looked at single nickel metal hydride batteries, I'm going to look at drill batteries, and I have 2 nickel metal hydride powered drills which are A, old and B, cheap, because everybody else is using lithium ion, I know, but anyway we're going to have a look at some multi-cell batteries and see how our charging testing system does on those. So that's it for this video, and I'll see you next time. So for now it's goodbye from Triplicate.
Goodbye.
It's the little things that get you down. Like, why did whoever designed this board, having put convenient holes, mounting holes in, not leave enough room round them to get a screw or a nut on? So that's however long it takes me to muck around filing down, sanding down plastic nuts to fit in. Hey ho, onward and upward.